Okay, take it away when you're ready.
Okay, great. So I want to talk about Tim's adventures in quantum mechanics. And you may think that I might as well have introduced this as now about something completely different, but I hope I'll manage to convince you that it's all connected somehow. Now, before I get to the quantum mechanics, I want to briefly tell you how I met Tim, not just because it's been a long day and we could all need a drink, but also because it provides some context to what I'm going to talk about later. So Tim and I met at a meeting from the Royal Society of London, which was about artificial intelligence. Now, I don't know anything about artificial intelligence. Sorry?
Can you hear me? Oh, okay. So I don't know anything about artificial intelligence, but, well, they paid the flight to London and the dinner was free, so I went. And Tim introduced himself as something with clouds and artificial intelligence. And so I thought, well, weather and climate, and put him in the drawer. Now, he came later and wanted to talk to me about free will in quantum mechanics. And I said, no, though I hope I did it a little bit more politely. And thought this was a little bit too weird. That might have been the end of the story. But a few months later, I had kind of a little existential crisis, which was that I'd run out of research funding, and I had concluded not for the first time that I should make a little more money with writing about science. Now, I normally write about theoretical high energy physics. There are only so many people who care about it. So I thought I should write about something that more people are interested in. For example, climate science. That's what everyone wants to read about these days, right? Problem is, I don't know anything about climate science. So I looked into my climate and weather drawer, and sure enough, there's this guy Palmer. Maybe I should talk to him. And so before I did this, I thought I'd better try to find out something about the man. So one thing that I found out was that he had actually written me an email 1 year earlier about his theories for quantum mechanics, which I'd put into my folder for people who sent me their theories of everything. Didn't reply to it. So I looked him up on Wikipedia, which has a very long list of titles and awards and everything, which didn't impress me. It says more about me than about him. Then I shook the internet a little bit more, and I found this interesting photo with an interesting article about it, from which I learned a couple of things. For example, he rarely cooks, but he can. Isn't any good at bricklaying. And interestingly, he plays guitar in a rock and roll band. And so I thought, well, that settles it. I definitely have to talk to the man. And he agreed on an interview pretty much immediately. And so I'm trying to follow, and for all I can tell, he talks about clouds. Clouds, clouds, clouds. Now, I know a lot of you would fit into my weather and climate drawer, but for what I'm concerned, it's either cloudy or it isn't. I don't distinguish 25 different types of clouds. Also, on that day, my recording software wasn't working, so I actually had to take notes by hand. Tim is not a slow talker, so that was quite one challenge. And I'm taking notes thinking, this is the most boring story I've ever worked on. No one will want to run it. And then he says, it's not like this is string theory. We know the equations. And I think, that's brilliant. I'm going to send it to the New York Times. Because why not? And would you know it? They actually ran it. They said yes pretty much immediately. And here we go. It's not like this is string theory, said Timothy Palmer. We know the equations. Okay, so I was really proud of myself. Then I realized I made it in 2 weeks from not knowing anything about climate science to writing for the New York Times about it. That's quite a career. My God, what if I wrote something wrong? So I sent the link to Tim, and then I'm chewing my nails for 2 hours, waiting for him to reply. And he says, only my mother caught me. So I concluded for this, I guess I didn't screw up the thing with the clouds too badly. And I agreed to look at his papers on quantum mechanics. This brings me to the second part. Why did he want to talk to me about free will? So he keeps sending me some of his papers and I read all of them. I'm pretty sure I've never seen any of those papers, but I can't shake the feeling that it sounds kind of familiar. And this didn't make sense to me until he sent me a copy of this paper, which I believe that's actually a scan of the actual physical paper dating back to 95. And I realized immediately, I've seen this paper before. I probably read it when I was a student. And the reason I remember is that I remember looking at this figure thinking it's probably the most crappy figure that was ever published in a scientific literature. But I was also thinking, at least there's one person in the world who's not completely insane. It is probably not a coincidence that 25 years later, my views on quantum mechanics are very similar to Tim's. So why the thing with free will? So I try to give you the briefest of all brief introductions to hidden variables models to explain the observations that are normally attributed to quantum mechanics. So imagine you have a laser that you send to a detector, and there aren't any purple lasers. The red would clash with the color beam of the slider and was just really ugly. So you send a laser to the detector and the detector goes bling. So far, so unsurprising. You can put a mirror there and send the laser to the other detector and the other detector goes bling. Okay, now I want you to imagine that this isn't a full laser beam with lots and lots of quanta of light, but it's just a single quantum of light. It's just a single photon. It would be pretty much the same story with the mirror and so on. But now what we do is we put a beam splitter there. Beam splitter, as the name says, splits a beam. And what this does is pretty easy to interpret if you're thinking of a full beam of photons. But what happens if you have only one photon? Well, quantum mechanics says actually the photon goes in both directions at the same time. And then when you measure it, pling, it's just on one side or the other. That's the collapse of the wave function. Now, in a hidden variables model, you're trying to come up with a local explanation for this. There's no non-local spooky action at a distance where this wave function suddenly collapses. So what do? Well, you introduce your hidden variables, and I've scaffolded this because they are called hidden variables, but it doesn't mean that they are necessarily unobservable. You know how it goes with nomenclature, it doesn't always make sense. So you introduce your hidden variable, and you say, well, depending on what the value of the hidden variable is, it either goes to the one side or the other. Not so complicated. But now the problem is, what do you do if you recombine those beams? So you put another beam splitter there, and this is what's called a Mach-Zehnder interferometer. So you get constructive interference on this detector, and the other part, which goes out to the top right, is empty. You could put another detector there, but nothing would go there. So how do you explain this with your hidden variable? You previously said, well, depending on what the hidden variable is, it either goes left, right. Now, to make this work, you actually need an interference from the two paths. So it can't go either one path or the other. Well, it's not so difficult. You just need a hidden variable that depends on what you're going to measure. If you measure which path the particle goes, you use the one type of hidden variable. And if you measure the interference, you use another set. And what this does is it violates the statistical independence between the hidden variables, that's the lambda and the detector setting. Could be 2 detectors, could be 5 detectors or 28, doesn't really matter, but normally people use 2 because of the types of experiments that they make. And this is just the simplest example that you can look at, which is easy enough for me to put on a PowerPoint slide, but you can do the same thing for any experimenting quantum mechanics. You can always explain it locally with hidden variables, but what you need to do is that the distribution, probability distribution of the row of the hidden variables needs to depend on what you're going to measure. And this is what's called superdeterminism. That's when this equality is violated. And this equality is called statistical independence. It's also known as measurement independence, or the free will or free choice assumption. So this is, I assume, why he wanted to talk to me about free will. Why is it known as the free will assumption? I've honestly no idea. I went and tried to make sense of the literature on the topic. It's a little bit mysterious how this came to be related to free will. I believe what's happened is it's a combination of two slight mistakes. One is that a lot of people assume that the hidden variables are associated with the particle that one prepares and that one wants to measure. That's actually not the case. So the hidden variables are just something that determines the outcome of the measurement. In the simplest case, and that's so simple that most people don't think about it, it's just the outcome of the measurement. So if I tell you the outcome of the measurement, you can predict the outcome of the measurement. The other problem is that people often read this equality or violation of the equality as a statement about a causation instead of a correlation. Now, if you get these two things wrong, you arrive at the weird interpretation that the hidden variables in the state that you try to measure somehow cause the detector setting. So they seem to interfere with the ability of the experimenter to freely choose the setting. And this is why it's sometimes referred to as the free choice or free will assumption. But I think it's really just a false interpretation of what this equality or its violation means. So this brings me to Bell's theorem in a nutshell. Bell's theorem is widely used to explain why nature has to be non-local in some sense. Now, I just told you can actually explain our observations with the local hidden variables model. So how does this fit together? A lot of you have probably seen the headlines of from the Nobel Prize this year for experiments that supposedly show that nature is really non-local. Well, that's just wrong. So this all goes back to Bell's theorem, which is an inequality that we know is experimentally actually violated if you make a measurement. So if you want a description of nature that actually agrees with our observations, then you need to have some theory that violates Bell's inequality. And what this means is you need a theory. If you have a completion of quantum mechanics by way of hidden variables, it either respects statistical independence, then it has to be non-local, or it's local, but then it has to violate statistical independence, and then it's super deterministic. And now I would say, well, obviously you don't want to throw out locality, because that's the major feature of Einstein's theories of special and general relativity. That would be completely insane. But that's the way that physics has developed since the 1970s when Bell discussed the matter. And there have been very few people who have paid attention to this option to actually keep the theory local. There have been some very general evaluations of the situation in the 1980s. There has been a toy model by Brown, and then there has been Tim papers, and then in the late 1990s there has been Gerard Tourte, who has his cellular automaton model that he also says is super deterministic. I'm actually not entirely sure it's super deterministic, but he says it is. So it completely understudied the possibility. Now, what does it have to do with what we talked about previously? So this is how I think it fits together. A measurement in quantum mechanics is non-linear. If you think about what I told you previously with the laser going to the detector, you send the laser to the one detector, then this detector goes pling. You send it to the other, and that detector goes pling. You send it through the beam splitter, it creates a superposition, so that's just the sum of the two directions. Now, if this theory was linear, then it should give you superposition of the plinging detectors, which isn't something that we ever observe. So instead, it's either the one or the other detector that goes pling. So that's a nonlinear process. Nonlinear systems can be chaotic. They don't have to be, but in this case, I think it's plausible that it actually is chaotic, because that explains why the outcome of a quantum measurement seems to be random. We haven't seen any irregularities. Chaotic systems have attractors. Chaotic attractors have gaps. And gaps create correlations. And here's the probably best known example of a chaotic attractor. You've all seen this before. I'm really just showing this because I've spent too much time on this animation. So the important thing about this, one thing is, of course, this isn't actually the attractor. It's just a curve that's infinitely close to gets very close to the attractor. But the important thing about the attractor is that it's not space filling. So it has gaps because it's a attractor. And I believe this is the reason why Tim made this, what he calls the invariant set postulate. So the invariant set is basically the attractor of some chaotic dynamical system. We don't know the equation, but maybe we don't need it. We can just talk about the properties of this set. And that it has gaps is one of the major features, I'd say. And I've noticed that people have some difficulty following this argument, so I'll try to illustrate this with a little figure. So what you see there, those two axes, those are two variables, doesn't really matter what it is, and there's some probability distribution. So the brighter on the left side, the higher the probability. Now, if I were to ask you, are those two variables correlated? You would say yes. Well, that's kind of obvious that, it's not a random distribution. There is some correlation between them. Now, what you can do is you can put a finite number of points in this graph with a probability distribution that you get from this continuous case. And that gives you a distribution of points like the picture on the other side. And now what you can do is you can take a uniform probability distribution and put it on the points and ask, what's the correlation between the two variables? Well, it's a good approximation, exactly the same as in the previous picture. The more points you sprinkle there, the better you will reproduce those correlations. And now the point is that there is no correlation in the distribution on the points. It's a uniform distribution. The entire correlation that you get between the two variables comes from the structure of the space, which is now just a set of points. And it's for the same reason that you can use the structure of the underlying space to create correlations that you find in bell-typed experiments. And Tim showed us in a number of papers how you could do this, a certain fractal structure on Hilbert space, which gives you exactly the correlations that people observe in various experiments. And that's not an interpretation of quantum mechanics, it's actually a modification. It's a more fundamental underlying theory, and it does make some predictions for experiments, which have not yet been done, but hopefully they will one day be done. And yeah, so we wrote a popular science article together because I guess we agree that, of course, locality should be respected. And we tried to make our case. We also ended up writing a few papers together. But what you all really want to know, I guess, is why I was so interested that he plays the guitar, is because I sing, not particularly good, but good enough if you cover it up with a guitar. So when the COVID pandemic hit, we did end up recording a song together. We're actually not in the same room together. This is the magic of photoshopping. And you can look this up on YouTube if you're interested. And I want to finish with a somewhat cryptical reference that maybe the Germans in the audience will understand. There's a somewhat silly but very well-known German song that's called Life Starts with 66. So from this reference point, you know, almost 4 years old. And I think that's exactly the right age to finish your theories on quantum mechanics. Thank you for your attention.